May 3rd, 1999. Dr. Josh Wurman stands beside his Doppler on wheels radar truck on a dirt road in north-central Oklahoma, watching his computer screen with a mixture of awe and disbelief. The numbers scrolling across the display are unlike anything he has ever recorded. The tornado churning across the farmland in front of him, a massive rain-wrapped wedge more than a mile wide, is producing wind speeds that seem almost impossible. His radar is measuring rotational velocities exceeding 300 miles per hour. The tornado's circulation is so large that it dwarfs anything in the scientific literature. He keys his radio and says, "We are looking at something historic here. This might be the largest tornado circulation ever measured." What Dr. Wurman does not know yet is that this tornado, striking near the tiny community of Mulhall, Oklahoma, will be overshadowed within hours by its more famous sibling, the Bridge Creek Moore F5, that will kill 36 people and become one of the most documented tornadoes in history. The Mulhall tornado, despite potentially being larger and possibly even stronger, will fade into relative obscurity, remembered primarily by researchers and tornado enthusiasts as the biggest tornado ever measured, the giant that history forgot. To understand how this remarkable tornado came to be, we need to rewind to the days leading up to May 3rd, 1999. Meteorologists at the Storm Prediction Center were watching a severe weather pattern develop across the southern plains that had all the characteristics of a major tornado outbreak. A powerful upper-level trough was digging into the region, bringing strong jet stream winds exceeding 120 miles per hour at 30,000 feet. At the surface, a strong low-pressure system was developing over the Texas Panhandle, drawing incredibly rich Gulf of Mexico moisture northward into Oklahoma and Kansas. By May 2nd, dew points across central Oklahoma were climbing into the upper 60s and low 70s, creating extremely humid air that, when heated by strong May sunshine, set the stage for an explosively unstable atmosphere. The morning of May 3rd dawned sunny and warm across Oklahoma. Temperatures quickly climbed into the 80s under partly cloudy skies, but meteorologists knew this pleasant weather was deceptive. By afternoon, convective available potential energy values were forecast to exceed 4,000 joules per kilogram across central Oklahoma, an enormous amount of instability. At the same time, wind shear values were off the charts. Surface winds were blowing from the south-southeast at 20 to 30 miles per hour, while winds at jet stream level were screaming from the southwest at over 120 miles per hour. This combination created extreme speed shear and strong directional shear, the perfect recipe for violent, long-lived supercells. Around midday, the Storm Prediction Center takes an extraordinary step. They issue a high risk for severe weather across central Oklahoma, their highest threat level, and include a rare hatched area on their outlook map, indicating a significant probability of strong tornadoes. The forecast discussion uses unusually stark language, noting that all the ingredients are coming together for a major tornado outbreak, and that violent tornadoes are likely. Local National Weather Service offices coordinate with emergency managers across the state. Television meteorologists in Oklahoma City begin warning viewers that this could be a historic severe weather day. Storm chasers from across the country converge on Oklahoma, knowing the atmospheric setup is as good as it gets. By 4 p.m. Central Time, thunderstorms are beginning to erupt along the dry line, the boundary between dry desert air from the west and humid Gulf air from the east, across southwestern Oklahoma. One storm in particular, developing near the town of Chickasha, rapidly intensifies into a classic supercell. Within 30 minutes, it produces its first tornado near Amber, Oklahoma, a violent wedge that will eventually strike Bridge Creek and Moore, becoming an F5 and one of the most infamous tornadoes in U.S. history. But as dramatic as the tornado that struck Bridge Creek and Moore is, it is not the only monster being born that evening. Further north, a second supercell is organizing near the town of Kingfisher. At approximately 5:30 p.m., this storm begins showing strong rotation on radar. The National Weather Service issues a tornado warning. Storm chasers in the area note the storm has a massive lowered base and powerful inflow, air rushing into the storm from all directions. At 6:05 p.m., near the community of Dover, the first tornado touches down. It starts relatively weak, rated F1, damaging crops and farm outbuildings as it tracks northeast. But atmospheric conditions are so favorable that the tornado rapidly intensifies. By 6:20 p.m., the tornado has grown into a large wedge over 3/4 of a mile wide, with winds exceeding 150 miles per hour, F3 intensity. It is moving northeast at about 30 miles per hour through rural parts of Kingfisher and Logan counties, destroying farms and rural homes. Trees are snapped and debarked across wide swaths. Well-built homes are severely damaged, with roofs torn away and walls collapsed. But the tornado is still strengthening, still growing, and it is about to become something truly extraordinary. At 6:35 p.m., Dr. Josh Wurman and his team with the Doppler on Wheels project intercepted the tornado near the community of Mulhall in northern Logan County. The Doppler on Wheels is a mobile Doppler radar mounted on a truck designed to get close to tornadoes and measure their wind speeds and structure with unprecedented accuracy. Wurman positions the radar a few miles from the tornado and begins scanning. What the radar shows is breathtaking. The tornado has grown into a massive wedge, well over a mile wide, potentially as wide as 1.5 to 1.75 miles across at its base. The radar velocity data shows rotational winds of 302 miles per hour at approximately 100 feet above ground level, the fastest winds ever directly measured in a tornado at that time. But it is not just the wind speed that is remarkable. The size of the circulation is unprecedented. The tornado's core, the area of strongest winds, extends for over a mile. Even at distances of nearly 2 miles from the center, winds are still exceeding 100 miles per hour. The sheer volume of air in violent rotation is staggering. By comparison, most violent tornadoes have cores a few hundred yards wide. This tornado's circulation is so large, it is almost more like a hurricane embedded within a thunderstorm than a traditional tornado. Wurman and his team watch in amazement as the data streams in. They know they are recording something that may never be seen again. The Mulhall tornado at this peak intensity is rated F4, with estimated surface winds between 207 and 260 miles per hour based on damage. But here, the story gets complicated and fascinating, where official ratings and measured reality diverge. The F scale, and later the enhanced F scale, rate tornadoes based on damage to structures, not on measured wind speeds. Because the Mulhall tornado tracked primarily through rural farmland, there were limited structures in its path for damage assessment. The farms and homes it did destroy showed clear F4 damage, with well-built homes reduced to rubble, vehicles thrown hundreds of yards, and extreme tree damage. But the lack of substantial construction in the tornado's core meant that higher-end damage indicators that would confirm F5 winds were not present. This creates a fascinating scientific and historical dilemma. Doppler on Wheels measured 302 miles per hour at 100 feet above ground. Even accounting for the fact that winds at the surface are typically somewhat lower than at 100 feet due to friction, the surface winds were almost certainly exceeding 260 miles per hour, the threshold for an F5 rating. Additionally, the tornado's massive size, 1.5 miles wide with violent winds extending across that entire width, suggests an intensity and power that rivals, or potentially exceeds, many F5 tornadoes. Yet because it did not strike substantial structures at peak intensity, the official rating remains F4. This raises a question that tornado researchers and enthusiasts still debate. Was the Mulhall tornado effectively stronger than the Bridge Creek and Moore F5 that struck just hours earlier? The Bridge Creek and Moore tornado achieved its F5 rating based on damage, with well-built homes swept completely off foundations, and debris granulated and scattered. Doppler on wheels measured peak winds of 318 miles per hour in that tornado, higher than Mulhall's 302 miles per hour. But the Bridge Creek and Moore tornado was significantly narrower, with estimates around half a mile to 3/4 of a mile at maximum width. The Mulhall tornado's circulation was roughly twice as large, meaning the total energy and destructive potential may have been comparable or even greater, despite the slightly lower peak winds. Some researchers have suggested that if the Mulhall tornado had tracked through a densely populated area with substantial construction, the damage would have been at least as catastrophic as Bridge Creek and Moore, and possibly worse, simply due to the tornado's enormous size. A tornado over 1.5 miles wide, with F4 to F5 winds across its entire circulation, would destroy everything within that 1.5 mile swath simultaneously. That would be an area of devastation far larger than most F5 tornadoes create. But because Mulhall tracked through mostly rural areas, we will never know for certain what the upper limit of its damage potential was. What we do know is what the tornado did to the structures it encountered. Near Mulhall, several well-built farm homes were completely destroyed, swept off their foundations, with anchor bolts removed. At one property, a large 2-story brick home that had stood for decades was reduced to a bare concrete slab. The debris was scattered over a 1/4 mile downwind, with pieces of the structure granulated into fragments. A nearby barn, constructed of heavy timber and metal, was completely obliterated, with large beams thrown over half a mile. Vehicles on the property were picked up and thrown, with one truck discovered over 400 yards from where it had been parked, crushed into an unrecognizable ball of metal. The vegetation damage was equally extreme. Entire forests were leveled, with trees not just knocked down, but debarked, debranched, and in many cases pulled completely from the ground. The tornado left visible scars in the earth, where its most intense winds scoured away topsoil, exposing red Oklahoma clay beneath. Power transmission towers, massive steel structures designed to withstand extreme winds, were twisted and toppled. High-tension power lines were ripped down across miles of the tornado's path. The scale and intensity of damage in these rural areas was clearly violent, clearly F4 to borderline F5. But without dense construction to damage, the full extent of the tornado's power could not be definitively documented. As the tornado continued northeast past Mulhall, it began to gradually weaken. By 6:50 p.m., it had narrowed to about 3/4 of a mile wide and decreased to F2 intensity. It continued tracking through rural areas, still causing significant damage to farms and rural structures, but no longer exhibiting the extreme characteristics it had shown near Mulhall. At approximately 7:15 p.m., the tornado finally dissipated near the Kansas border after being on the ground for over an hour and traveling approximately 38 miles. Remarkably, despite its size and intensity, only minimal injuries were reported, and no fatalities occurred along its path, a testament to the rural nature of the terrain and the fact that warnings had been issued well in advance. But while the Mulhall tornado was dissipating in northern Oklahoma, disaster was unfolding to the south. The Bridge Creek Moore tornado carved a path of total destruction through suburban Oklahoma City, killing 36 people and causing over $1 billion in damage. It demolished entire neighborhoods, swept away hundreds of well-built homes, and created some of the most dramatic destruction ever documented. Television stations broadcast live footage of the tornado destroying homes in real time. The images were shown nationally and internationally. Bridge Creek Moore became the defining tornado of the outbreak, the one that would be remembered and studied for decades. The Mulhall tornado, by contrast, faded into the background. It had struck rural areas where dramatic damage footage was limited. It had caused no fatalities and relatively few injuries. It had not threatened major population centers. Despite being potentially larger and scientifically more significant than Bridge Creek and Moore, and despite the Doppler on wheels measurements representing groundbreaking research, It simply did not have the human drama and visual impact to capture sustained attention. Within days, when people talked about the May 3rd outbreak, they talked about more. Mulhall was a forgotten footnote. This is where the legacy of the Mulhall tornado becomes fascinating. In the scientific community, it is legendary. The Doppler on wheels measurements from that evening represented a quantum leap in tornado research. For the first time, scientists had quantitative data on the wind structure of a violent tornado at very close range. The measurements showed that the strongest winds were not necessarily at the center of the tornado, but in an annular ring around the core. A discovery that has implications for understanding tornado dynamics. The data revealed details about how wind speed varies with height in tornadoes, how the circulation extends horizontally, and how subvortices contribute to localized wind maxima. Research papers analyzing the Mulhall Doppler on wheels data have been published in major meteorological journals. The tornado is regularly cited in discussions about the largest tornadoes on record. When meteorologists compile lists of the widest tornadoes ever measured, Mulhall is always near the top. Its width of 1.5 to 1.75 miles is rivaled by only a handful of other tornadoes, including the 2.6-mile-wide El Reno tornado of 2013 and the 2.5-mile-wide Hallam, Nebraska tornado of 2004. The Doppler on wheels wind measurements from Mulhall stood as the highest directly measured tornado winds for over a decade, until being surpassed by measurements from the El Reno tornado. But outside of scientific circles and among tornado enthusiasts, Mulhall remains largely unknown. Ask most people about the May 3rd, 1999 outbreak, and they will mention more if they mention anything at all. The Mulhall tornado does not have a Wikipedia page of its own. It is mentioned only in passing on pages about the broader outbreak. There are no documentaries focused on it, no books written about it, no memorial services held annually. It is the forgotten giant, the record breaker that few remember. This disparity highlights an important reality about how we remember disasters. Tornado fame, if such a thing can be said to exist, is determined not by scientific measurements or even by intensity, but by human impact and visual drama. Bridge Creek and more killed 36 people and destroyed neighborhoods on live television. Mulhall measured winds of 302 miles per hour and was possibly the largest tornado ever recorded, but it killed no one and damaged mostly farms and forests that do not make for compelling TV footage. In the public consciousness, death toll and visible destruction trump scientific significance. Yet from a pure meteorological standpoint, the Mulhall tornado represents something perhaps even more remarkable than Bridge Creek and more. It demonstrates that under the right atmospheric conditions, tornadoes can grow to almost inconceivable sizes. Circulations over 1.5 miles wide, with violent winds across that entire span. It shows that our understanding of what constitutes an extreme tornado is still evolving. Most F5 tornadoes have been relatively compact, with cores a few hundred yards wide. Mulhall suggests that tornadoes can achieve violent intensity while also being massive in scale, combining the worst of both characteristics. The tornado also raises uncomfortable questions about rating systems. If a tornado has measured winds exceeding 300 miles per hour, but does not encounter substantial construction, should it be rated based on theoretical damage potential or only on observed damage? The current system rates only on observed damage, which makes sense from a consistency standpoint, but can lead to tornadoes with extraordinary Doppler measurements being underrated relative to their actual power. Some researchers have proposed supplemental rating systems that incorporate Doppler measurements, but implementing such systems is complicated and has not gained widespread adoption. For the people who lived through the May 3rd outbreak in Oklahoma, the distinction between Mulhall and more was perhaps less important than the shared experience of surviving one of the most violent tornado outbreaks in United States history. That evening, dozens of tornadoes struck Oklahoma, including multiple violent ones. Over 40 people died statewide. Thousands of homes were destroyed. Entire communities were devastated. Whether the tornado that passed near your home was the biggest ever measured or just an F4 mattered less than whether your family survived, whether your house was still standing, whether your life would ever be the same. For residents near Mulhall, their tornado was plenty big and scary enough. Several families lost their homes completely. Farms that had been in families for generations were destroyed. Livestock were killed. Years of work building and maintaining properties were erased in minutes. The fact that their tornado set scientific records, or was potentially the largest ever documented, was small comfort when sorting through rubble trying to salvage anything from a lifetime of possessions. Today, over 25 years later, the physical evidence of the Mulhall tornado has largely disappeared. Farms have been rebuilt. Trees have regrown, though the forest canopy still shows gaps. The land has healed in the way that rural land does, slowly but steadily. But in the scientific literature, the Mulhall tornado lives on as a benchmark. It is the tornado that showed us what is possible at the extreme end of the scale. It is the data point that expanded our understanding of tornado size and intensity. It is the giant that proved giants can exist. The debate about whether Mulhall was effectively stronger than Bridge Creek Moor will likely never be fully resolved. Both were extraordinary tornadoes produced by the same outbreak under the same exceptional atmospheric conditions. Bridge Creek Moor had higher measured peak winds but was significantly smaller. Mulhall had lower peak winds but was roughly twice as wide with violent winds across its entire circulation. Which represents the stronger tornado depends on how you define strength, peak wind speed, or total destructive potential. What's not debatable is that May 3, 1999, demonstrated that when atmospheric conditions align perfectly, nature can produce tornadoes that push the boundaries of what we thought possible. The fact that two tornadoes of such extreme characteristics occurred within hours and miles of each other speaks to just how favorable the environment was that evening. It was a once-in-a-generation setup, perhaps a once-in-a-century setup, that produced once-in-a-generation tornadoes. The legacy of the Mulhall tornado is ultimately a story about perspective. From a scientific standpoint, it is one of the most significant tornadoes ever documented, the largest tornado circulation ever directly measured, a data goldmine that advanced tornado research by years. From a public awareness standpoint, it became a footnote to Bridge Creek Moor, overshadowed by a more photogenic and deadly tornado that struck just hours earlier. Both perspectives are valid. Both are incomplete without the other. Perhaps the lesson of Mulhall is that not all superlatives translate to fame. The biggest is not always the most remembered. The most scientifically significant is not always the most publicly known. And sometimes the most extraordinary events fade from collective memory simply because they occurred in the wrong place at the wrong time, overshadowed by other extraordinary events occurring simultaneously. The Mulhall tornado was the biggest tornado ever measured. It was 1.5 miles wide, with 302 miles per hour winds that carved through the Oklahoma countryside, and hardly anyone remembers it. That is its story. That is its legacy. The forgotten giant, the record breaker in the shadows, the biggest tornado that history overlooked.